Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's presentation on Poisson distribution, Part 1. In the last session, we have discussed about the binomial distribution in which the parameters are n and p, where n is the number of trials and p is the probability of success. And the formula in binomial distribution is probability of x successes is given by NCx p power x q power n minus x, where x from 0, 1, 2 and so on n values. Now coming to today's presentation, today I would like to introduce the Poisson distribution and also derive the mean and variance of Poisson distribution. Now coming to the introduction part of Poisson distribution, the Poisson distribution was introduced by a French mathematician Simon Denis Poisson in the year 1837. It is a discrete probability distribution similar to binomial distribution. Poisson distribution is also a discrete probability distribution. These two are discrete probability distributions. So in Poisson distribution, parameter lambda is the parameter of the Poisson distribution, which is a positive value. And now Poisson distribution is suitable for rare events. That means in which the number of trials n is very large, and the probability of success p is small. That means as n tends to infinity and p tends to 0, then we apply the Poisson distribution. So the Poisson distribution is suitable for rare events in which n is very large and probability of success is very small. And some examples of rare events: the number of accidents in a particular junction. Similarly, number of printing mistakes in a book of 100 pages and number of defective items in a lot of items. So these are rare events. Now we apply Poisson distribution when n tends to infinity and p tends to 0. That means the number of trials n is very large and probability of p is very small. Just now we discussed in the previous slide. Now the probability function in Poisson distribution is given by the probability of x successes using the formula e power minus lambda power x by x factorial. So the probability of x successes is given by e power minus lambda power x by x factorial. Here x is the number of successes, x denotes the number of successes, and this lambda is the parameter which is a positive value, and this lambda is called the parameter of Poisson distribution. And mean of Poisson distribution is mu equal to lambda and variance is sigma square equal to lambda. That means the mean and variance of Poisson distribution coincides, both are equal to lambda. Now since we have the formula to find the probability using Poisson distribution, now we can define the Poisson distribution. It is a distribution of discrete random variable capital X, which has the probability function. Probability of x successes is e power minus lambda power x by x factorial when x takes the values from 0, 1, 2 and so on up to infinity. So here we can take x values, it's not infinity, a very large value, and 0 otherwise. And now Poisson distribution can be derived as a limiting case of binomial distribution with the substitution lambda equal to np. So Poisson distribution can be derived as a limiting case of binomial distribution with lambda equal to np, where p is very small and n is very large. And also we can derive the recurrence relation in Poisson distribution as probability of x plus 1 successes is equal to lambda by x plus 1 into probability of x successes. So that means if we have probability of 0 successes, we can find the probability of 1 success. Put x equal to 0 here, which is lambda by 0 plus 1 into probability of 0. So if we have the initial value probability of 0 successes, we can generate the remaining probabilities. Similarly, probability of 2 is lambda by substituting x equal to 1, we can get probability of 2. So 1 plus 1 into probability of 1. So use this probability of 1 here, and similarly use probability of 2 to find probability of 3, lambda by x plus 2 plus 1 into probability of 2. So, using this recurrence relation, we can find the successive probabilities of x values. Now, coming to the derivation of mean and variance of Poisson distribution. Now, let us derive the mean and variance of Poisson distribution. So, the mean and variance of Poisson distribution. First, the mean. Now, what is the formula to find the mean? Mean is given by mu equal to expectation of x. So, mean is mu equal to expectation of x. Since x is a discrete random variable, here x into p of x, where x from 0 to infinity. Now, let us substitute the probability of x successes using Poisson distribution. The formula is e power minus lambda, lambda power x by x factorial. So, let us substitute here x into e power minus lambda, lambda power x by x factorial, where x from 0 to infinity. Now, let us simplify this. So, sigma x equal to 0 to infinity, x into, we can write this e power minus lambda outside of this summation since it is a constant value, lambda power x by x factorial can be written as x into x minus 1 factorial. So, which is e power minus lambda into sigma x equal to 0 to infinity, these two gets cancelled, lambda power x by x minus 1 factorial. Now, to get a particular form, let us substitute, put x minus 1 equal to some y. Then, the mu is given by e power minus lambda sigma x equal to 0 to, here this becomes x equal to 1 to infinity, because we will get negative value here. So, x equal to 1 to infinity, lambda power, here x minus 1 is y. So, what is the value of x? Y plus 1 or 1 plus y by y factorial. So, this is e power minus lambda sigma. This can be written as lambda into lambda power y by y factorial. Now, we can take y from 0 to infinity. So, this lambda we can write outside, which is a constant, lambda into e power minus lambda sigma y from 0 to infinity, lambda power for y by y factorial. And what is this expression? This is the expansion of e power lambda. So, these two gets cancelled and we get the mean of the Poisson distribution as lambda. Similarly, we can derive the variance. So, variance of Poisson distribution, sigma square. Now, what is the formula of variance? Expectation of x square minus expectation of x whole square. This is the formula of variance. Now, here we can write this as x square into p of x from 0 to infinity minus expectation of x. Just now we have calculated the expectation of x is lambda, mu equal to expectation of x equal to lambda. So, let us substitute that here, lambda square, and this LHS, let us in the first term, let us substitute the formula here, e power minus lambda, lambda power x by x factorial minus lambda square, and here e power minus lambda constant. So, we can write outside of the summation, and what remains, x square lambda power x by this x factorial can be written as x into x minus 1 factorial minus lambda square. Now, that implies here x remains lambda power x by x minus 1 factorial minus lambda square. Now, let us to simplify this, let us rewrite this value of x as x minus 1 plus 1 into lambda power x by x minus 1 factorial minus lambda square. So, this x minus 1 plus 1, just I am adding and subtracting 1 here, just for our simplification purpose. Now, multiply x minus 1 into lambda power x by x minus 1 factorial, this is first term, plus 1 into, so lambda power x by x minus 1 factorial minus lambda square. So, e power minus lambda into, now this one, the first term x minus 1 lambda power x by this denominator x minus 1 factorial can be written as x minus 1 into x minus 2 factorial plus this is lambda power x by x minus 1 factorial minus lambda square. And again simplifying, we get here these two gets cancelled. So, lambda power x by x minus 2 factorial plus lambda power x by x minus 1 factorial minus lambda square. Now, similar to the previous derivation, here put x minus 2 equal to y and put x minus 1 equal to z. Then x will be y plus 2 and z will be z, and here x will be z plus 1. So, by substituting these two, we get sigma square equal to e power minus lambda into lambda power x. In the first term, x is y plus 2, lambda power y plus 2 by y factorial, and in the second term, x is z plus 1. So, plus lambda power z plus 1 by z factorial multiplied by minus lambda square. So, e power minus lambda, here we have sigma notation into lambda square, we can write outside of this sigma because lambda square is a constant, and what remains, lambda power y by y factorial plus here lambda remains constant. So, you can write outside, and lambda power z by z factorial minus lambda square. So, here this term is nothing but the expansion of e power lambda plus the here again the same, the expansion of e power lambda minus lambda square. So, let us multiply lambda square e power minus lambda e power lambda plus lambda e power minus lambda e power lambda minus lambda square. These two gets cancelled. So, what remains? Lambda square plus lambda minus lambda squares. Again these two terms will be cancelled and we remain with lambda. Hence, the mean of Poisson distribution mu equal to lambda and variance of Poisson distribution is sigma square equal to lambda. Hence, the mean and variance of Poisson distribution coincides. So, in the today's session, I have introduced the Poisson distribution, which is a discrete probability distribution in which the probability of x successes are given by e power minus lambda, lambda power x by x factorial, and here lambda is the main parameter of the Poisson distribution. So, if we have the value of lambda, we can calculate the probability of any number of successes because the formula is involving that lambda and this x is the number of successes. So, in the next session, we will discuss some problems on Poisson distribution. And this Poisson distribution is applied only when n tends to infinity and p tends to 0. That means n is very large and p is very small. Such events are called rare events. In the case of rare events, we apply Poisson distribution. So, in the next session, we will solve the problems involving such rare events. Thank you very much.